Good afternoon, everybody. We're going to continue on talking about equilibrium. And we worked through some problems, and hopefully some numbers are starting to make sense and combining with Le Chatelier's principle. And so we're going to talk about the equilibrium constant today. And then in class, we're going to start working through some equilibrium problems. So application of the equilibrium constant, we can predict the tendency of a reaction to occur. Is it really going to happen or not? The concentration represented at equilibrium for part 2, and then the equilibrium position achieved from a given set of initial conditions. Now, again, we're talking about the tendency. We are not talking about the speed. They are not going to be related. And the other thing that we need to remember when we were talking about K now, our equilibrium constant, remember, is equal to the concentration of our products over the concentration of our reactants. Okay, so this shift, where are we going to understand this in terms of our equilibrium constant? So if we figure out that K is greater than 1, we're going to talk about, sometimes that K is going to be given, a lot of sometimes we'll calculate it. It just depends upon the type of problem. But if we look at it and K is going to be greater than 1, so then you need to think about that my reaction is going to have to shift to the right at equilibrium. We have more product than reactant when I have K is equal to 1. So at equilibrium, the reaction shifts right. And this means that I have more product than reactant. And I think that you probably can think of some different situations, making ammonia for one, when I want it to shift to the right because I want more product than the reactant if I'm going to develop something. And so another term that they might use here, if K is greater than 1, that K is in favor of the products. That's another word that you will see there if it favors one side or the other in terms of equilibrium. And in this situation, my reaction often goes to completion. So I think you can imagine that if the reaction is going to be going to completion, it probably never, it doesn't ever really reach equilibrium. I'm trying to force it to go to completion, so I'd want my equilibrium constant to be very large if I'm really concerned about obtaining a certain product. Then on the other side, if K is going to be less than 1, then it's going to be pretty much the exact opposite. So at equilibrium, the shift is going to be to the left. So I need some more reactants to sustain that. And K is in favor of the products. Of the reactants. So K is in favor of the reactants, and I'm not really producing hardly any product. And in this situation, the reaction often may not even occur. So then if you are in the engineering world and you see that your K is much less than 1 and you really feel like you have the right concentrations of the products or reactants to make a product, then you probably need to start changing the conditions. Do I have to take a look at the pressure? Do I have to look at the temperature? Do I have to look at my container? And so those are all factors that you're going to take a look at depending upon which way your reaction is shifting. So remember that the size of K and the time required to reach equilibrium are not related. We are not looking at how quickly that is. We are just basically looking at the constant, the equilibrium constant, period. Then we can also look at rate and time, but they are not they are not combined. The time required to reach equilibrium depends on the reaction rate, again the size of our EA, and we can change that by adding a catalyst, and the size of K determined by the energy factors between reactants and products involve entropy. So I've kind of already talked about that in one of the podcasts before. Now, how do we know which way we need to shift this? So we're going to use our reaction quotient, which goes on to our mass action that we were taking a look at in section 13.2, law of mass action. So it's used to determine the shift in the initial concentrations in order to reach equilibrium. Sometimes it'll be very obvious and you don't need to find Q, but many times you can't tell which way it's going to shift. So again, Q is going to be the same thing that we've been doing, our concentration of our products over the concentration of our reactants. So when you go ahead and calculate that out, then we're going to compare this to K to determine the shift. So if Q and K are equal, then there's not going to be any shift. There's not going to be any shift at all because if they're equal, I'm at equilibrium. Now, if Q is going to be greater than K, you can see that if Q is greater, by looking at products over reactants, I must have too many products. It's too large. So I need to shift it left in order to reach equilibrium. So we're going to shift left to reach our equilibrium. The concentration of the products is too high. So we need to consume some more products, form some reactants, so we're going to shift it to the left. All right, now if Q is going to be less than K, I think you can see is probably going to be the exact, not probably, it is the exact opposite, that I'm going to have to shift my equation to the right to reach equilibrium. And so here my concentration of my reactants are too large. And so we need to consume that to get some more products. And so the shift in equilibrium is something that when we start determining and calculating problems, we're going to start using the words ICE, I-C-E, and it's going to mean our initial concentration, our change, and then our equilibrium expression. We're going to be using this to determine and solve what our concentrations are of our products and reactants at equilibrium. Well, in order to solve this mathematically, we need to understand which way it's going to shift. So again, we're just applying numbers. Once we see numbers, for some of you, I think it'll make more sense. Others of you like the theory and the words behind it. That's what makes sense to you. So tomorrow we're going to start looking at how to solve these. You need to bring your math brains with you because we're going to be using quadratic formulas, square roots, and dropping things. So we need another little math lesson in here. All right, I hope you guys have a wonderful night, and I will see you soon.